במושב הזה יש לנו שתי הרצאות, and I think that now I need to move to English. So I'm very pleased that Professor Christian קיוכין from Basel, from the Sleep Laboratory in Basel, is with us today, and is going to address us in his talk in regards to sleep. It's many times very difficult to explain to people the damages of light. And we can talk about epigenetical damages, we can talk about secretion of melatonin and light and circadian rhythms, but it's very difficult to explain what does it mean. But I think it's very easy for people to understand if they sleep well or they don't sleep well. And I'm sure that all of us know if we slept well at night or we had a lousy sleep. And light has to do a lot with sleep. And if you are aware, in the last year, there are, even in the popular newspapers, not in scientific journals, but also in popular journals, many articles showing the connection between good sleep and lifestyle, life wealth. So I'm calling upon Professor Christian קיוכין, please. And thank you for coming to us.
It's a pleasure to be here in this country, and I can tell you I'm happy to see the sun, because in Switzerland right now I haven't seen the sun for 7 days. So we have really bad weather compared to you. And temperature-wise it's also much better here during winter. So I'm going to talk about, because I'm a biologist, my background is, I'm not an engineer, I'm going to talk about the effects of light on human sleep and also circadian rhythms. And circadian rhythms are probably not so familiar with you, so I'm going to explain what I think what circadian rhythms are, and also a little bit on cognition. Cognition means how well your performance is during the day, how well you can perform tasks and multiple things, not only tasks, but also how you feel during the day, how sleepy you feel, how alert you are. Now I just want to start with a quote by Professor Seisler from the Harvard Medical School. He recently did in Nature, where he says that light impacts on our circadian rhythms more powerfully than any drug. So we don't know any medication which is so strong like light and affects circadian rhythms. And if you would approve light as a medication, I think it would be very difficult to get it approved by the FDA in the US, because it has so many implications on our behavior that it's very difficult to approve. Now, if you look at circadian rhythms, so we have circadian rhythms are about the day rhythms, and we can measure this in different hormones, we can measure it in sleep-wake behavior, but light actually affects different kinds in this circadian rhythm. So you can change the phase of your rhythm, or you can also change the amplitude by light, and even the waveform of your rhythm you can change by light. And I'm going to give you some examples. The most prominent one is, of course, phase changes by light. So here you're looking at a person in the sleep laboratory who stayed 4 days in our sleep lab, and you can see the secretion of melatonin, which is a hormone which is high during the night. And when you give light here in the second night, let's say we simulated a night shift, so someone was exposed to 6.5 hours of light, you can see what happens. This peak here at 4:45 in the morning shifts much later, and 3 days later the peak is 8:21 in the morning, so you induced a so-called phase delay of more than 3.5 hours in this person. And this can happen when you have too much light during a night shift, for instance. So that's the effect of light on circadian phase. What is less known is also the effects on circadian amplitude. It's another person here. Again, you're looking at his melatonin rhythm. and he experienced 3 night shifts where we gave them 3 night pulses, and you can see here we stopped the clock for 32 hours in this case. In another person just below, subject 1757, we gave 2 night pulses during the night at the critical zone, and for 55 hours we don't have any melatonin secretion anymore. So that means that we can not only change phase, but also the entire pattern, also the amplitude of the circadian modulation. And last but not least, we also adapt to photoperiodic changes. I'm not sure whether in Israel you have very large seasons, but in Switzerland, of course, the days are much shorter during winter as compared to summer. And if you look at the melatonin profile again, you can see that the melatonin secretion is much wider if you have a larger dark period as compared to the summer days below here. And this is a classical experiment done by Tom Baer already back in the 90s. And this is not only true for melatonin, this is also true for other hormonal rhythms. On the right hand side you can see the cortisol secretion also adapts on the photoperiodic changes. So in other words, light has a strong circadian impact which we should be aware of. But besides this circadian, light can also have acute effects which are probably not circadian. And I just listed some of them. We know for a while now that light can acutely suppress melatonin, this hormone I just showed you before, in minutes. And this is probably not circadian. We also know that light can activate or inhibit, sleep-promoting neurons in hypothalamic areas which are really important for sleep induction. And light on the other side can also activate wake-promoting orexin neurons, which is a new neurotransmitter which has been discovered 15 years ago, which is a very important neurotransmitter in the brain to make you more awake. And there is really good indications from animal data that light can acutely affect these things. And you know this probably, there is a new photoreceptor system in the eye which is called melanopsin, and the photopigment is called melanopsin, and this photoreceptor sits in the ganglion cells, and it's different from rods and cones, and we assume, of course, that this melanopsin receptor is probably a very good key player, or the main key player, to transmit these non-visual responses of light. And the interesting thing about this is that this photoreceptor absorbs light at around 460, 480 nanometers, so in the blue range. And by the way, only 1% of these ganglion cells are actually photoreceptives. So we have a lot of ganglion cells which don't absorb light at all, or which are probably not functional. Now, to illustrate this in a animal setting, that's here, for instance, if you give light to a nocturnal animal, in this case a mouse, you make them sleepy. So light makes us more alert, but a nocturnal animal, it makes them sleepy. And you can see, as soon as you switch on the light at time 0, the animal goes to sleep, and it stays asleep as long as the light pulse is on, and then it goes. So if you switch off the light, it's going to be awake again. So it's like a switch, a sleep switch with light. And if you manipulate, so that's the wild type animal, if you manipulate these melanopsin ganglion cells I just mentioned before by destroying them with a neurotoxin, this response is completely abolished. So that really indicates that this melanopsin photoreceptive element is a key element in transducing this evoked acute effects of light on sleep in this animal. And the question, of course, is this also true for humans? In humans, you cannot destroy melanopsin, which is unethical, of course, but what you can, of course, you can manipulate the light source. You can play around with the wavelength, because if melanopsin absorbs into blue range, it may be that we also have a more blue shifted response, and I'm going to show you some results about that. So, as I said before, in contrast to the animal, we don't sleep when we see the light because we are a diurnal species. So light for us means wakefulness, it's an alert state. And here you are looking at the dose-response relationship of the alerting action of light. So we used different illuminances, so we went from 0.5 lux to 10,000 lux. And you can see this relationship is somehow sigmoid, so it means that half of the maximal alerting response of light you already get with around 120 lux. So we are rather sensitive to light, and this was polychromatic light, so the full spectrum in this experiment. But since I showed you before that it's probably the blue range which is important, we started to test that already 15 years ago, no 10 years ago, sorry, now 15 already, by applying monochromatic light sources with different wavelengths. In this case, we compared 460 nanometers with 550 nanometers. And for all of our measurements we did in the lab, so we gave them this light exposure in the evening, we saw a superiority of this short wavelength line, which means, I wouldn't call it superiority, but for instance, as I told you before, melatonin was significantly more suppressed by blue light in comparison to 550 nanometers, but also gene expression, PER2 gene expression, which is a circadian clock gene we measured in the oral mucosa, was highly more significantly activated with the blue light, and also subjective sleep, so they felt more alert under blue light. And when we looked at sleep in the following sleep episodes, they had less slow wave sleep when they had the blue light condition. Slow wave sleep is deep sleep, so it's the amount of deep sleep which is a very important sleep stage for to recover from the waking day. So this was a clear indication that blue light is more powerful, and then of course you can ask, but is it only because we use this very specific monochromatic light, which is not a natural light, you never experience, or an artificial light either, you never experience monochromatic light during the day. So we extended our studies, and we also tested fluorescent lamps, energy saving lamps, here in the second panel in the middle, and you basically get the same response. So if you we only had 40 lux, by the way, so very, very low illuminance levels here in this panel. And again, if you compare 6,500 Kelvin with 2,500 Kelvin, there was a significant more alerting response to the blue enriched light. And also, when we then move to computer screens, as you know, the computer screens, they have LEDs, which have a very strong blue portion. Also then people felt more alert. Now in terms of sleep, I told you before that when you look at sleep, we didn't induce, because I'm a sleep researcher, we didn't induce insomnia. So we didn't induce a sleep problem in these people acutely. Maybe also because these were also very good sleepers. And if you take good young sleepers, they can just sleep in any situation. So we have probably some kind of a ceiling or a floor effect in our data. But when we carefully analyzed the time course of EG delta activity during sleep, which is again an indicator of how deep you sleep, we always observed that, and this is taken here, so these are 6 hours, so they usually sleep 6 to 7 hours in the lab. And then you see this decline in this delta activity, which basically indicates deep sleep is going down, and it's getting, your sleep is getting more superficial during the night. But what we discovered was that in the first sleep cycle, there was a significant reduction in this measure. After bright light, after monochromatic light, and also after blue and rich light, which is a clear indication again, yes, indeed, deep sleep is reduced, particularly in the first sleep cycle. But people didn't realize that. So when we asked them in the morning, how well did you sleep last night, there was no significant change. So subjectively, they could not actually feel this light effect. Now, another questions we had, besides alerting, besides sleep, are there also other cognitive functions affected by light? So we call these higher cognitive functions. And in other words, does light make you bright in the evening? And for that, we used the computer screen study. And the background was, of course, we spent more and more times in front of computer screens. You know that the displays are becoming larger, especially the TV sets in our days. And many displays are equipped with LEDs in our days. And what is the light intensity or illuminance is probably not as strong, but you are sitting very close to it and it's directly directed towards your eyes, so it has probably some impact on your physiology. And to do that, we asked people to come to the lab to do an evening shift of 6 hours. So they came around 5 o'clock in the afternoon and they stayed until midnight in our lab, and the other day they came again, or a week after, and in one condition they used the LED backlit computer screens indicated here on the right side here, and I cannot even distinguish it from here. So they look so similar, they couldn't tell whether they are sitting in front of an LED or not. But when you measure this, of course, you have much more blue light. In this case, 2/3 more blue light in the range of 440, 480 nanometers. And in terms of illuminance, it was almost the same for both conditions, 80 to 100 lux. And we actually didn't expect a lot of changes. And some colleagues told me, don't do the study, you won't find anything. But we did it anyway, because when you measure carefully in the lab, you see some effects, and this is melatonin again. You see the melatonin rise in the evening, which usually takes place 2 to 3 hours before you go to sleep. So if you are well entrained from a circadian perspective, you should go to sleep when your melatonin starts to rise, or let's say 2 to 3 hours after. And what you see here, there was a decrease during the LED screen condition, and we measured a delay of the onset of about 60 minutes, which is quite considerable. So it's a phase delay, we call it, of 1 hour, and this was only one evening shift. So you can imagine if you do several evening shifts, it could shift you probably even further. And then, as I said before, because we were interested in cognition, we also measured the incidence of slow rolling eye movements. You know that when you are very tired, your eyes are becoming very slow and they're rolling, and it's very hard to keep them open. And so it's a very good indicator of sleepiness. So it's a good objective marker, and you can clearly see in the LED condition these slow rolling eye movements were suppressed. And also frontal EEG activity, which is brainwave activity in frontal brain regions, was much more suppressed in the LED condition, which is indicative of a more alert state. But also higher cognitive functions were affected. So they were better in sustained attention and response control, which involves working memory tasks and also frontal brain regions. So it's not only alertness which is better, but also your higher cognitive functions are better when you use these LED screens in the evening. And also, when you look at declarative learning, they had to learn word pairs. They were much better by correctly identifying new word pairs, which we included in this task. So higher cognitive functions are also affected by LED. And now you can say, is it a beneficial effect, yes or not? Well, in my view, it's not. If you do this every evening, you're probably going to disturb your sleep, as I said before. But if you do it maybe just once or twice a week, then probably it's okay. But you shouldn't do it in the evening, because your circadian system thinks it's day, and that's why they are more alert, and you can even induce phase shifts. So this really is in line with recent study where they put people in the MRI scanner, so they scan them during the task with different light conditions, and you see here that not only hypothalamic areas, which are here in green, are activated by this blue light, but also other brain areas in the brainstem, the locus ceruleus, which is a very important wake-promoting area. So if this area lights up, that means you are really awake. and also the amygdala and the hippocampi are relevant areas for performance, for memory, and also emotion regulation. So it's a very complex effect, as I said before, but also cortical areas are, of course, activated, the cortical areas which are implicated in the task which they are going to do in the scanner. Now, of course, if you want to prevent blue light in the evening, because as I told you before, we use computers more and more, and if you look at in adolescents, at least in Switzerland, they spend more and more hours in front of these tablets and smartphones on average, and this is statistics from the Kaiser Foundation in the United States. It's 53 hours per week, and it's not going down, it's increasing, and it's not only kids and adolescents, I think also adults are spending more and more time in front of these tablets. So one way, if you cannot prevent youngsters from being in front of these tablets in the evening, we ask them to block this, let's say, blue portion of the light by applying orange tinted glasses you can buy. And you see these so-called blue blockers, they block out a lot of light, not only the blue portion in my view, it's going up into the green range. So there is still some room for improvement for these blue blockers in my view. And we asked them to wear them for 1 week at home. We checked them because we had a sensor in the glasses whether they really wear them, so the compliance was really good. And after 1 week they came back to the lab and we measured their melatonin levels, we measured their sleepiness levels and so on, and the control group was exactly the same glasses with clear lenses. And what you see here in this graph is again this melatonin increase I showed you before, and you can clearly see when they had the clear lenses, when they had the blue light, melatonin was lower. When they had the orange tinted glasses, melatonin started to rise earlier and was higher. This was exactly what we expected and we wanted to see. And what was also nice is that the kids, or these youngsters, they felt sleepier after the orange tinted glasses, right before they went to bed. So they had they were sleepier and they could also then sleep faster. So it works. It's a little bit complicated and you cannot really ask people to wear these glasses, but this is another measure we did, the performance, which is objective reaction time task. They were much significantly slower when they had the orange tinted glasses. Now, some of these non-visual or non-image forming light effects are very different among people. And we started to look into this very recently, where we wanted to know, is age an important factor or gender an important factor, or are even some polymorphisms in genes, because genes are very important in circadian biology and sleep, whether they also play a role. I'm just going to show you in the last part of my presentation some of these examples. Here I concentrate again on melatonin secretion because I showed it before. When you are a young person, you have much higher melatonin values during the night as compared to the older. This is here, this comparison, and these older people are really healthy. Older people from the Swiss mountains, I have to say, they're really sportive. Some of them are really, in terms of physical shape, in a better shape than the youngsters, but still, it's a natural decline in melatonin secretion during the night, which is common. Now, we sleep deprived them for 40 hours, so they had to stay awake, otherwise we couldn't have measured this in saliva. And then we sleep deprived them again with light at 250 lux to see, because 250 lux, it's a moderate light. It's not very bright and it's not very dim. But we were interested whether it influences your melatonin secretion, and it does, but only in the young people and not in the older, here in red. So this is indicative that age plays an important role in, for instance, the melatonin suppression by light. This is probably due to the yellowing of the lens with age, and also the pupil size, of course, changes with age. And also if you look alertness, so this is the alertness curve over 40 hours. So when you sleep deprive people, of course they get sleepier and sleepier, and there is a circadian modulation of sleepiness. But in the youngsters, this 250 lux was significantly alerting, whereas in the older it was not. So this is a clear example that age plays a role if you look at non-visual light effects in the workplace, for instance. It really depends whether your shift worker is 50 or 30. Another interesting thing, in my view, we discovered, not only we, are the gender effects. So when we did the fluorescent lamp light study with 6,500 Kelvin and 2,500 Kelvin, we noticed that all women didn't like the blue enriched light. Maybe that's a cultural thing, maybe it's different here. But if you look at the distribution, over 90% of the women preferred the warm light, and for the men, it was not such a problem, but they actually went rather for the 6,500 Kelvin solution. So if we ask them which light would you buy in the shop, and a lot of men tell me that they cannot buy LEDs in the shop because their wife at home doesn't like it because it's too blue enriched for them. And then, of course, we were interested whether this has something also to do with the reaction to light. And you can see here there was an almost significant interaction between gender and the alerting effect of light. So in women here on the left-hand side, the blue light was not alerting, whereas in men it was significantly alerting. And also when you look at reaction time, only the man showed this significant decrease in reaction time. So it's a decrease in reaction time. Going up is better, but not the women. Yes?
The question was for people in Switzerland that you asked men and women.
Yeah.
Because if you ask in Israel, the results will be different.
Yeah, I think so. I think there is also a cultural component. If you go to Italy already, there is more blue enriched light, and there is. But in Switzerland, no one. I'm not sure whether it's more the northern part of Europe. If you go to Sweden, it may be the same like here. Yeah. So it's the opposite, so that women prefer blue.
No, let's say most of people like warm white.
Warm white.
Yeah, 2700 is the most common demand because we are full of light, because of the sun, I believe. Full of sun most of the time. People are more related to the warm white. This is actually we can see on selling what is the main demand. It's almost 70%.
The warm light. Good. Other questions? No? Yeah, so I'm just telling that maybe the gender I mean, even when you measure it in the lab, you can see changes. We didn't see changes in melatonin suppression, I have to admit. So everyone suppresses melatonin the same, independent of gender. Last but not least, that's a little bit a complicated thing, but in sleep research, we are interested in so-called genes which are affecting our sleep-wake behavior. And there is a polymorphism or a variant in a so-called PER3 gene, which is related to chronotype. So if you are a carrier of the PER3-55 variant, so there are three variants, but we only tested two. So there is a 5-5 type and a 4-4 type. And if you happen to be a 5-5 type, you are probably more an earlier type. So you wake up, your sleep-wake preference is earlier. So there is a correlation between we call it chronotype, late and early types, and this polymorphism. And also, when you are a 5-5, you have probably more intense sleep, so more deep sleep, and you suffer more to the detrimental effects of sleep deprivation. Which means when you are on shift work, the 5-5s, they are much worse at performing at work than the 4-4s. Now I exaggerated a little bit, but that's the tendency a lot of people see in the literature, and also we could confirm some of these results. So this seems to be one of the candidates which is playing probably a role in how well you sleep and how your chronotype is. Now the question, of course, could some of these effects be explained by a differential response to light in these 5-5 and 4-4 individuals? And we actually tested this in the lab, and we found out that also the genotype, and if you look again, here is again melatonin suppression, the 5-5 suppressed much more under blue light than the 4-4s. They didn't show any significant reaction. And if we also looked again at the more objective measures of sleepiness, the alerting response was also stronger in the 5-5. So even on the genetic organizational level, we see changes in the non-visual response to light. Well, I think I'm at the end, and I would like to summarize my talk just again to say that non-visual effects of light can be seen from genes up to very complex, we call it neurobehavioral performance, such as higher cognitive functions. Even light levels below 40 lux affect human circadian physiology, so we need to be careful also for low light levels, but only when they have a strong blue portion, and probably only in young people. And some of these effects are age and gender dependent, and even dependent on genetic polymorphisms. So the take-home message, I think it's not new for you, is that you should be really careful when you select your lamps and computer screens, because it can impact on your circadian physiology, sleep, and it doesn't depend whether it's at home or in the working phase. Well, I would like to thank my collaborators at the Center of Chronobiology. All of them are PhD students or postdocs, and of course the funding companies. I hope they still support us in the future. And if you want to download PDFs from our website, you are welcome to do that. We have full PDFs of all of our publications, and I would like to thank you for your attention. Thank you very much. Well, I can take questions, no problem.
Any questions? Okay, so
There is one.
Why we need polyphenol, what you said before? Melatonin, why we need it?
Why we need melatonin?
Yes, why we need it?
Well, melatonin is a hormone which is secreted during the night and it's under the control of the circadian clock, so it's a very good indicator of your circadian rhythm. And it's also implicated in, it's not needed for sleep, but if you have melatonin, so if melatonin is coming in your body, you are going to dissipate heat, and you are going to relax, and it's like fluffing the sleeping pillow. So it's a sleep initiator, a natural sleep initiator, so to speak. And if you don't have it, like if you have a spinal injury here, then the transmission doesn't take place anymore, then you have a bigger chance of having sleep problems. But it's not an urgent need. You can sleep without melatonin, but it's good to have.
Any more questions? Yeah.
Are there certain people or some of the population? Are there certain people or some of the population which is not affected by the light? I understand it's affected through the retina. The new receptors are not there or damaged in some way, and
Yeah.
they will not react in the form you mentioned.
Well, it's a very good question. I mean, it would be nice to have patients with are circadian blind but not visually blind, and vice versa. And there is a paper out there showing that totally blind people can still have a circadian photoreception, and they can still tell whether the light is on or off, but only when they have 460 nanometers. They don't see the light, but they're...
The blue spectrum.
Yeah, just in the blue spectrum. And this so-called non-image forming part of the light has probably still some visual information which we not consciously see. But if you have patients, I would be happy to study them, because my dream would be to have someone who has no melanopsin, but the rods and cones and vice versa. But it's ophthalmologists don't even know about this new photoreceptor. Some of them, at least.
No more questions? I have two questions. Questions. You are talking about screen of computer TV. What about LED when you walk in the street and you are exposed to it, or it clicks into a bedroom, and we are exposed to it during our sleep without knowing it, but it penetrates from the outside.
Well, we didn't do any studies in the field, of course, but I would expect if the LED is strong enough, you would see similar effects. That's my hypothesis. But you have to be careful because there was a study now showing that from the TV sets, because they're now larger, they also have LEDs and they couldn't see effects, but this was because people were sitting 5 meters. So if you are not, it needs some distance. Yeah, the distance is important also.
The second question is, if you have you can distinguish by the genes, by the pair 3, between O's, the one that goes to sleep late, and the last, the one that goes to sleep early. Can it be used, for instance, when you need to select people for shift working? They should take, because now you know the chronotype would not.
Well, I'm not sure whether it's ethically correct. At least in Switzerland, you cannot select people according to your genotype, not yet. The thing is, it would be probably more ideal, but you also have, if you are a 5-5, it's not only the chronotype which is important, they are also more susceptible to the effects of sleep deprivation. So if you sleep deprive a person like this, he or she is doing not a good job. So for fighter pilots, probably it's much better to select on the genotype and not for shift workers. But and we have to be careful. There's a lot of variation. So it doesn't mean that when you are a 5-5, you are 100% an early chronotype. So one has to be very careful. So the variance explained is probably 20-30%, but not more.
Okay. So thank you very much.
Okay, thank you very much. Appreciate it.
Thank you very much for coming and being with us.
Thank you.
Lovely lecture.